Hello APC Mechanics students, today we'll solve the past paper FRQ 2021 set 1 exercise 3. And then let me start and say a triangle. So always remember that the figure appears to be above the text and not below the text, okay? So always restrict yourself whenever you're doing a text to look at the figure above. A triangular rod of length capital L and a mass capital M has a non-uniform linear mass density. So this is very important. What does this mean? It means that the center of mass is not located geometrically at the center of the object. Given by the equation lambda is gamma x squared, where gamma is 3m divided by L cube, and x is the distance from point P at the left end of the rod. Now, before I read part A, because simply the mass distribution is not uniform, then we need to, if it's not given, we need to find the rotational inertia using calculus as well as for the position of the center of mass. And indeed in part A they're telling us using integral calculus show that the rotational inertia of the rod about an axis perpendicular to the page and through the point P, so basically P would be the pivot, is given by 3/5 ml squared. So the first thing that we do, we set our integral correctly. You should remember that I is given by the integral of x squared dm. And now this should be a bounded integral. How do we set our boundaries? First we need to choose the origin, always and forever in such type of cases, to be the pivot itself, so that would be the origin. And if you notice carefully, they gave you the position x to be 0 and the final position to be L. We need to integrate over all the mass around the origin, so starting from 0 to L, so that would be 0 to L. For example, if the origin was given or the pivot was given here, then because this is an origin and the position might be positive and negative, and suppose this distance is given by 2L/3, then we need to integrate from minus L/3 into 2L/3. Okay, so this is a position that might be positive or negative, and here the positivity and negativity plays a role in how the mass distribution is located around the pivot and taking into consideration cancellation effect. Now here our integral consists of two variables x and m, and because the boundaries are set in terms of position and it's difficult to change them in terms of mass, then it's easier for us to change m into position using the linear mass density. So let me say, but lambda is given by dm divided by dx, and we're interested in the value of dm since we know lambda. Then in this case dm is given by lambda dx, which is basically gamma x squared dx, and we know the value of gamma to be given by that. So now we can rewrite our integral as I, which is integral from 0 to L of x squared gamma x squared dx. Gamma is a constant which depends on this, we can drag it out, and that would be gamma integral from 0 to L x power 4 dx. Now gamma is given by 3m divided by L cube, and the integral of power 4 would give us power 5. Now we need to compute this once at L and once at 0. We can ignore the 0, so that would be 3m divided by L cube into L power 5 divided by 5. Now this would cancel, that would be L squared, so it's given by 3/5 ml squared. And remember that the rotational inertia has a dimension of kilogram meter square, which is in agreement with this. Then in this case the rotational inertia is given by 3/5 ml square. And here no need to worry about the parallel axis theorem, because the integration itself counters that part if our origin is chosen at the pivot. Moreover, let me mention the following remark. Here you cannot apply the parallel axis theorem, considering the fact that you know the rotational inertia around the center and shift it toward the point P, simply because the mass distribution is not uniform. The only way to do it is via an integral. Now in part B, they're asking us to determine the horizontal location of the center of mass of the rod relative to point P. Express your answer in terms of L. Then again we need to perform integration, and the position of the center of mass is given by the following relation: the ratio of two integrals. Again, we need to integrate from 0 to L based on our choice of origin. So from 0 to L, Now the upper integral is given by x dm, and the lower integral is given by the integration over the total mass. Now we have determined the previous part, the infinitesimal mass, to be given by gamma x square. So that would be integral from 0 to L of x gamma x squared dx divided by the integral from 0 to L of gamma x squared dx. Now in the numerator and the denominator, gamma as a constant can be dragged out, so that would be gamma integral from 0 to L x cubed dx divided by gamma the integral from 0 to L of x squared dx. The biggest mistake that you can do here in such type of exercises is to simplify the x's. Remember that the x's are included inside the integral, and here you need to take into consideration the priority of operations. So the priority is for the integrals, then you can do cancellation. However, omega is a constant independent of x. We have dragged it out and we can cancel it. Now x cubed would be x power 4 divided by 4 computed from 0 to L, and that would be x cubed over 3 computed from 0 to L, so that would be L power 4 over 4 over L cubed over 3, and that would be 3 over 4 multiplied by L. Then the position of the center of mass is given by 3 over 4 L, indeed is expressed in terms of L, and the previous, so let me say here, what does the center of mass to be 3 over 4 L means? That the center of mass is located in the right region here, more shifted toward the end of the rod. So it's more away from the pivot. Now in part C, they're telling us for an axis perpendicular to the page, is the value of the rotational inertia of the rod around the point P greater than, less than, or equal to the value of the rotational inertia of the rod around the rod's center of mass. So what they're telling us here, so the rotational inertia of the rod around the point P greater than, less than, or equal to the value of the rotational inertia of the rod around its center of mass. So they're trying to compare two rotational inertias. One, we're calling it IP, which is the rotational inertia around P, and another one, which is ICM, which is the rotational inertia around the center of mass. So in the case of IP, the axis of rotation is given here, and in the case of ICM, the axis of rotation is given here. So because now we know that the center of mass is given at this location, which is 3 over 4L. Now in this case, we know that the rotational inertia around the point P is greater because our center of mass is located here, which means more average mass is being away from the axis of rotation. In case for the ICM, because more mass is being distributed around the center of mass, this would reduce the rotational inertia. Whenever the rotational inertia is away from the pivot, this will cause I to increase. Then let me say greater than, and remember that even if you didn't, you were able to justify your answer properly, don't leave anything for, choose any one out of these, because there is no penalty for a wrong answer, and they would give you a mark for the correct choice. Now let's justify properly. Since on average the mass distribution is farther from P, than the center of mass, so here I'm trying to state that the mass is distributed away from P and closer to the center of mass, then the rotational inertia through P is greater than the rotational inertia through the center of mass. Now, on the next page, the rod is released from rest. This is very important, and the initial speed is 0. And the rod is released from rest in the position shown, and the rod begins to rotate about a horizontal axis perpendicular to the page and through point P. Part D, on the axis below, sketch the graphs of the magnitude of the net torque on the rod and the angular speed omega of the rod as function of time from the time the rod is released until the time its center of mass reaches its lowest point. And here, so you can directly know how would the graph of tau and omega be. Now you can think always about the net torque as the angular acceleration alpha, and remember we need to plot the magnitude, so no need to worry about the minus sign. So if we're talking about the position of this rod when it's left, now you can think about that as passing through the equilibrium position, it will start to perform oscillations. And whenever we're talking about oscillations, we know that the shape of the position would be something like that, a sine function, or even a cosine function. Now here what I'm trying to say, because we are plotting the magnitude, then the shape of the curve would be either something like this, which is going up, or something like this, which is going down. No need to worry about these shapes. Okay, so one of them, so here if we're trying to plot tau, which is alpha, and omega, one of the shapes would be like this, and one of the shapes would be like this. Okay, so if you think about it, while the rod is going down, so these are trigonometric functions associated with such type of motions, basically for very small amplitude that would be harmonic motion. So these are the type of the curves. If you think about it, because the rod is going down, the speed would increases, so omega would represent such type of curves, and the acceleration would represent this one, and this always happen whenever any object is being left to fall freely and accelerate or rotate freely under the influence of gravity. So the torque would be something like this. And the angular speed would be something like this. Okay. So as the center of mass reaches the lowest point, which is basically the equilibrium position. Alright, now part E, as the rod rotates from the horizontal position down through the vertical, is the magnitude of the angular acceleration on the rod increasing, decreasing, or not changing? Now again, we're talking about when the rod goes from the horizontal to the vertical, and here we can notice that because the angular acceleration is directly proportional to the net torque according to Newton's second law, then it would be decreasing, because according to this curve it's decreasing. However, here we will try to justify an answer not based on the graph in order to have a more general response, because answers to such type of questions or an AP exam, they are not very straightforward. Okay, so what's happening here basically? Let's check. Now we know that it's decreasing, but why the angular acceleration is decreasing? Now the center of mass initially located here, we can treat this rod as if it's just a point. So center of mass, all the mass is concentrated here. Now this distance is 3L/4. Now all of that is not important. After time evolves, the center of mass would be occupying, for example, this position, and that would be the radial direction, that would be the tangential direction. Okay, now this is the angle theta, that would be again the angle theta here, and that would be pi/2 minus theta. The pull of gravity is down. If this is the horizontal, this is the vertical, then this is again theta. Now why I'm doing all of this? Because we know that this is accelerating, so changing in speed due to the influence of gravity, and the torque produced by the gravity is being the force, which is mg, multiplied by the distance, which is whatever, 3L/4. We don't care about all of this because this is constant. What we care is about the angle, which is here, or the projection. We need to project the force along the tangential, and that would be cosine theta. As the rod is moving down, if you can think about it, theta is opening more and more until it reaches pi by 2. As theta is opening more from 0 to pi by 2, which means that cosine theta is decreasing. But the thing is that we cannot explain all of that and write it down. That would be very difficult for us. However, there is another definition for the torque is related to the lever arm. So basically also the torque is related to the perpendicular distance from the pivot to the force itself, which is this distance. And as you can notice that when the center of mass is going down to the equilibrium position, this distance is indeed decreasing, right? Because the center of mass is approaching the equilibrium point. So if you consider another point here, as time evolves, when the center of mass is rotating down, this perpendicular distance from the pivot to the center of mass is decreasing, and we call this distance to be the lever arm, which is also related to the definition of the torque. So as the center of mass is going down, the lever arm is decreasing, which decreases the net torque due to the gravity, and for this reason the angular acceleration will decrease. Then let me state here, since the horizontal position of the center of mass of the rod is getting or moving closer to the axis at P, then the lever arm for the force of gravity, which is basically producing the net torque, is decreasing. So the magnitude of the angular acceleration decreases. And now moving on to the last part of this exercise. The mass of the rod is 3 kg, so we know the mass, and the length of the rod is 1 meter. We need to calculate the linear speed v of point S as the rod swings through the vertical position. Now we know that whenever we're talking about speed of a free rotating body, it's more intuitive that we think about energy. And whenever they tell us to calculate or to determine the expression of alpha, we need to do it using Newton's second law for rotation. Now, before doing the energy, as usual, we need to take our P level, and this is always done by taking the P level to be the horizontal passing through the center of mass in the final position. So let me say here the final position is vertical. So let me say the following. Take the P level, to be the horizontal, passing through the center of mass and the final position. and the final position basically is the vertical position on the rod. Now, why this is important for us? Because this will assure that the final gravitational potential energy would be 0. And now, because we're applying a big law, let me say apply conservation of energy. And we're gonna say that energy initial is equal to energy final, and energy is about being kinetic and gravitational. And if you remember that at the beginning of the exercise or somewhere I have pointed out that it's released from rest, and based on our choice that would be 0. Now let me denote the mass to be capital L mgh. Now we will worry about h after a bit. That would be half I omega square. Now I is given by, if you recall, to be 3/5 ml square. So let me say, okay, that would be half 3/5 ml square. And here we need to check whether we need omega or the linear speed. Indeed, we need the linear speed, and we know that omega is related to the linear speed by v/r, but we need to specify for which point we're calculating the speed. Since we're calculating the speed at the end of the rod, then we need to replace r by capital L. Then that would be v squared divided by L squared. Now mg, h here in this case, it represents the distance from the initial position of the center of mass to the PE level. And remember that the PE level has been chosen at the position of the center of mass in the final position. So the center of mass is given by 3/4 L, which is here. And initially the rod was somewhere here in the horizontal position. Now that's 3L/4. So basically, let me say again, h is the distance from the initial position of mass to the PE level. And in this case, you know that this distance is given by 3L/4. So you see that always h is important to determine it carefully. So that would be 3L/4. And now after we have done so, the problem is easy. It's about cancellation effect. And here remember that you can directly anticipate the answer, because we're talking about the linear speed of a body which is freely rotating under the influence of gravity. Then we expect that omega should be a coefficient multiplied by g/L, and the speed would be given by a coefficient multiplied by Lg. So that's the only unique way to construct speed and angular speed. Now L square cancels with L square, m with m, 3 with 3, then 4 with 2, that would be 2, then g/2 is equal to 1/5 v square. And you see, notice, so because I know that mine would be something multiplied by gl, so I have remembered that here I have an L. So in this case, v square would be given by 5/2 Lg or gl, which means that v is the square root of 5/2 multiplied by gl. And plugging this expression on the calculator, knowing that the length L is given by 1. Here notice that they gave us the mass, but no need for the mass. This is always a trick in AP. And the answer would be given by, so the length is 1. Then in this case, the linear speed of the point S in the final position is almost given by 4.95 meters per second. And that's it for me in this video, guys. See you soon in a new one.